Welcome back to Physics 371 Online. Today, I'd like to do a very brief introduction to the new topics from Chapter 3 in the textbook. They all fall under the heading of Special Techniques for Finding the Electric Potential. And we're going to start today with a somewhat abstract, but actually very useful discussion of solutions to Laplace's equation. Our goal in electrostatics, ultimately, is to find the electric field of a charge distribution. Because if we know the electric field, then if some other charge comes into the vicinity, we can calculate the force it experiences, and then use all the apparatus of kinematics to figure out the subsequent motion of that particle. So, there's several ways of finding the electric field of a charge distribution. We can always come back to Coulomb's law. Or, more easily, we can find the electric potential, which itself is a scalar. And we start with the charge distribution, find the potential, and then take minus the gradient of the potential to find the electric field. However, there are lots and lots of cases, many of which are described in Chapter 3, where both of these methods are either difficult or even downright impossible to use in an analytical form. So we're going to learn several alternative methods, some of them approximate ones, that will allow us to find the potential of a charge distribution. In differential form, the problem we're really trying to solve is this. Del squared V is minus rho over epsilon 0. And we said before that that's called Poisson's equation. And so the simplest possible version of Poisson's equation would be in a region of space where there's absolutely no charge. And if rho is equal to 0, then Poisson's equation reduces to Laplace's equation, which we see here written down in Cartesian coordinates. Solutions, v of x, y, and z, to Laplace's equation are called harmonic functions. Now, let's look at the properties of solutions to Laplace's equation, first in one dimension, and then we'll generalize to the cases of 2 and 3 dimensions. In one dimension, we really just have the second derivative of v with respect to x equal to 0. And the solution to that equation is really simple. We need a function v where the second derivative gives us 0, and v, that's the equation of a general straight line, is the solution to that equation. Note that since we have a second order equation, there are two independent constants, m and b, that have to be determined by the application of boundary conditions. So, consequently, since we see the solution here, v of x has the following very simple but interesting properties. The first is that v cannot have any extreme points, which means a maximum or a minimum, except at the boundaries of the x domain. And that is just obvious by looking at the linear character of the solutions. In between the ends, there will never be a maximum or a minimum. The second property says that for any constant value r, the electric potential at a given point is half, or the average, of the sum of the electric potential at nearby points, points that are displaced from x by a constant amount r. So we can generalize these properties to the case of solutions to the 2 and 3-dimensional Laplace's equation. All of these properties can be proven, but we're simply going to state them here and then make use of them. In 2 dimensions, we've got Laplace's equation, which doesn't seem like it's that much more complicated, but now realize that we have a partial differential equation. And since it's a partial differential equation, there's no easy way to write down the general form of a solution. However, we can show by analogy to the case of 1 dimension that valid solutions, v of x and y, must obey, first of all, the fact that no extreme points exist except at the boundaries of the xy domain. And it's pretty easy to see why here, because for an extreme point, the definition of an extreme point is a point where the slope is equal to 0, and then the second derivative is either positive or negative, depending on whether the function is a maximum or a minimum. So for an extremum, d squared v dx squared and d squared v dy squared are both either positive or negative, right? And so if they're both positive, they can't add up to 0. And if they're both negative, they also can't add up to 0. And so this effectively means that we can't have extreme points except the ones that exist at the boundaries. And the second property for solutions to a two-dimensional Laplace's equation is that if we pick a point xy and then define a circle of radius r around that point and integrate the quantity v times dl all the way around that circle and average it out by dividing by the circumference, we always end up with the value of v at the center of that region. In other words, the average of v around the circumference of a circle of radius r is equal to the value of v at the center. And just think about what v would be like if it indeed had maxima or minima. If there were a point in space where v was a maximum with respect to x and y, then if you drew a circle around that point and then averaged the values of v around that circle, if the point xy were a maximum, then the average values around the circle would all be smaller, and therefore the average would not give you the value at the center. Okay? However, it does. And so these harmonic functions are special kind of functions that have these properties. And finally, we can extend this to the case of 3 dimensions, once again with our partial differential equation in x, y, and z. This one is even worse. We have very little hope of writing down a general solution to this, and so we're going to learn techniques for solving special cases. Once again, valid solutions to this equation must obey the two by now familiar principles that there are no extreme points except at the boundaries, and secondly, in this case, having a three-dimensional system, we can define a sphere of radius r centered on a point xyz. And we find that taking the value of v on the sphere, adding it up, and then averaging over the surface area of the sphere gives us exactly the value of the potential at the point that's the center of the circle. And so this can be proven in the text for the region around a point charge, and then since any general charge distribution can be regarded as a collection of individual infinitesimal charge elements, the proof can be generalized to those kinds of charge distributions using the superposition principle. That's not a proof, but that is an argument that leads to a proof. So we've surveyed some of the fundamental properties of the solutions for the electric potential that satisfy Laplace's equation. But the solutions themselves, the specific constants that go into them, are determined by the boundary conditions. And so it's natural to ask the question, what kind of boundary conditions are required to specify a unique solution V? And by unique, we mean that there is one and only one solution. So what sort of boundary conditions are required? And it's very easy to prove two uniqueness theorems. The first uniqueness theorem says that the solution to Laplace's equation is uniquely determined if the value of v is a specified function on all the boundaries of the region. There could be special cases where v would simply be a constant, or even 0, on all boundaries of the region. But we don't have to have that, as long as v is a specified function, so that picking any point on the boundary, we know the value of v. As long as that's true, then we know there are unique solutions to Laplace's equation. For example, if we just use a little bit of diagram here, imagine a region of space, a three-dimensional volume, demarcated by this red surface, and if v is given everywhere on that surface, if we know what it is, then v inside is uniquely determined. That means there's one and only one v that satisfies Laplace's equation. So we will prove this in class. For a region containing conductors and filled with a charge density rho, there's a similar theorem. It's called the second uniqueness theorem, and it says in a region containing conductors and filled with charge density ρ, E is uniquely determined if the total charge on each conductor is given. Alright, so we have to know the charge density, but if there are conductors in the region, as long as we know the total charge on them, then we also now know that there are unique solutions to Laplace's equation. So imagine that the region of space is filled up with conductors that have total charge Q1, Q2, and then of course charge density in between of ρ. Then if that's the case, then we know solutions to Laplace's equation in that region are uniquely specified. And these properties, these uniqueness theorems, although they seem somewhat abstract, turn out to be very useful tools for the very next topic, which is called the method of images. I will see you in class.